Hey Bobcats, this is Mr. Peterson here. We're talking about today curve fitting with exponential and logarithmic functions. This section is really just going to talk about determining an exponential pattern, and when we get into class, we'll do a little bit more problem solving with this actual idea. But what we'll be doing essentially is modeling data and seeing if it can fit into an exponential or a logarithmic function. And we'll also be using exponential and logarithmic models to analyze data and make predictions. To start off, we should write down two definitions: exponential regression and logarithmic regression. You'll recall we've already done linear regression, and in linear regression is when we took a set of data points and we determined the line of best fit. And it's going to be kind of similar here, except with, as you know, with exponential and logarithmic functions, we don't have a line, we have a curve. So we'll be using data to try to determine the curve of best fit and deciding if it's exponential or logarithmic. So there's those two. Make sure you get those two written down. All right, so as you've probably picked up in class, the way to determine if a set of data is exponential is you've got to look for a constant ratio in the y values between equally spaced x values. So in other words, if we do the ratio of 2 to 2/3, well, that's really just 2 over 1 divided by 2/3, which is 2 over 1 times 3 halves, which is 6 halves, which is 3. Okay, well, what about 6 to 2? What about this value to this value? 6 to 2. Well, that one, of course, simplifies to 3. Well, what about 18 to 6? 18 to 6 simplifies to 3. We have a constant ratio between the y values of 3. In other words, it would always take multiplying by 3 to get to the next equally spaced y value. So if that's happening, you've got an exponential data set, and it will fit in the format of y is equal to a times b to the x power, where a is our starting value and b is our growth or decay factor. All right, so let's actually try some of this. So this first example is just recognizing whether or not we can write this data set as an exponential function. So let's look at a. All right. Well, if you're looking at a, you can see that we're adding 2 between the equally spaced y values. We're always adding 2. If you look at the ratio of the y values, -1 to -3, that's 1/3. +1 to -1, that's -1. So we didn't have a constant ratio of the y values, but we did have adding 2 each time, which means that this is a linear function. This is a linear function over here. All right, well, let's try b. Remember, we want to look for a constant ratio of the y values of equally spaced x values. All right, so let's just try. You know, what would we have to add to get from here to here? Well, we'd have to add 1/2. Well, what would we have to add to get from here to here? Well, we'd have to add 1. What do we have to add to get from here to here? We have to add 2. All right, so that should give you a clue right now that this is not linear. All right, so let's try the ratio of the y's to the y's. So if we do 1 to 1/2, well, that really becomes 1 over 1 divided by 1/2, which is 1 over 1 times 2 over 1, which is 2. All right, let's try this one. 2 to 1. 2 to 1, that's 2. Let's try this one. 4 to 2. Well, that's 2. So this is an exponential function, and we could set it up in the form of y equals ab to the x. And in this case, our growth factor would be our constant ratio, 2. All right, so let's try a couple problems. There's one problem. And here's another one. And when you get to class today, we'll talk about data sets and how we can use our graphing calculators to look at data sets and then do an exponential regression on them. All right, thanks, guys. See you in class.